Good day everybody. So in this video, we will deal first with the major types of pollutants and their sources. In the remainder of the chapter, pollution in rivers, lakes, and groundwater is discussed, placing the emphasis on the categories of pollutants found in domestic wastewaters. For both rivers and lakes, the natural factors affecting water quality will be discussed as the basis for understanding the impact of human activities on water quality. So water pollutants and their sources. The first one is what we call the point source. The wide range of pollutants discharged to surface waters can be grouped into broad classes. Domestic sewage and industrial wastes are called point sources. Why? Because they are generally collected by a network of pipes or channels and conveyed to a single point of discharge into the receiving water. Domestic sewage consists of waste from homes, schools, office, buildings, and stores. The term municipal sewage is used to mean domestic sewage into which industrial wastes are also discharged. The second one is the non-point sources. Urban and agricultural runoff are characterized by multiple discharge points. These are called non-point sources. Much of the non-point sources pollution occurs during the rainstorms or spring snowmelt, resulting in large flow rates that make treatment even more difficult. Non-point pollution from urban stormwater and, in particular, stormwater collected in combined sewers that carry both stormwater and municipal sewage requires major engineering work to correct. The next source of pollution is the oxygen-demanding material. Anything that can be oxidized in the receiving water with the consumption of dissolved molecular oxygen is termed oxygen-demanding material. This material is usually biodegradable organic matter, but also includes certain inorganic compounds. The consumption of dissolved oxygen, or DO, poses a threat to fish and other higher forms of aquatic life that must have oxygen to live. The next source of pollution is the nutrient. Nitrogen and phosphorus, two nutrients of primary concern, are considered pollutants because they are too much of a good thing. All living things require these nutrients for growth. Problems arise when nutrient levels become excessive and the food web is grossly disturbed, which causes some organisms to proliferate at the expense of others. Another source is the pathogenic organisms. Microorganisms found in wastewater include bacteria, viruses, and protozoa excreted by deceased persons or animals. When discharged into the surface water, they make the water unfit for drinking, that is, non-potable. If the concentration of the pathogens is sufficiently high, the water may also be unsafe for swimming and fishing. Another source of pollution is the suspended solids. Organic and inorganic particles that are carried by the wastewater into receiving water are termed suspended solids. When the speed of the water is reduced by flowing into a pool or a lake, many of these particles settle to the bottom as sediment. Organic suspended solids may also exert an oxygen demand, while inorganic suspended solids are discharged by some industries but result mostly from soil erosion, which is particularly bad in areas of logging, strip mining, and construction activities. The next one is salts. Although most people associate salty water with oceans and salt lakes, all water contains some salt. These salts are often measured by the evaporation of a filtered water sample. The salts and other things that don't evaporate are called total dissolved solids, or the TDS. A problem arises when when the salt concentration in normally fresh water increases to the point where the natural population of plants and animals is threatened, or the water is no longer useful for public water supplies or irrigation. High concentrations of salts are discharged by many industries And the use of salt on roads during the winter causes high salt levels in urban runoff, especially during the spring snowmelt. Of particular concern in arid regions where water is used extensively for irrigation is that the water picks up salts every time it passes through the soil on its way back to the river. In addition, evapotranspiration causes the salts to be further concentrated. Thus, the salt concentration continuously increases as the water moves downstream. If the concentration gets too high, crop damage or soil poisoning can result. The next one is the pharmaceuticals and personal care products. These are a class of compounds that are applied externally or ingested by humans, pets, and other domesticated animals. They are released to the environment through the disposal of expired, unwanted, or excess medications to the sewage system by the individual's pharmacies or physicians. Another source of PPCPs in the environment is through metabolic excretion. The excretion of the chemically unaltered parent compound and metabolized by products in urine and feces. Another one is the endocrine disrupting chemicals. The class of chemicals known as endocrine disruptors or EDCs alters the normal physiological function of the endocrine system and can affect the synthesis of hormones. Some naturally occurring EDCs, such as 17B estradiol, that is both a naturally occurring estrogen and a synthetic estrogen used as a method of birth control, are excreted into the wastewater. Other EDCs include the polychlorinated biphenyls commonly used pesticides such as atrazine and the other triazine chemicals and the phthalates. EDCs can mimic estrogens, androgens, or thyroid hormones or their antagonists, although the structures of many EDCs bear little resemblance to that of natural hormones with which they interfere. They can also interfere with the regulation of reproductive and developmental processes in mammals, birds, reptiles, and fish. The chemicals can also alter the normal physiological function of the endocrine system and can affect the synthesis of hormones in the body. EDCs can also target tissues where the hormones exert their effects. Pesticides. The major classes of pesticides are herbicides, insecticides, and fungicides. Herbicides are used to kill weeds. The most commonly used herbicides are atrazine, metolachlor, and alachlor. Chlorpyrifos, diazonin, and matalan are the typical insecticides used to kill insects that would otherwise destroy crops, gardens, or structures. Common fungicides are sulfur, chlorothalonil, and mancozeb. The most commonly occurring pesticides found in water were primarily those currently in use, whereas those found in fish and sediment are the organochlorine insecticides such as DDT that were heavily used decades ago. The last source of water pollution is the heat. Although heat is not often recognized as a pollutant, those in the electric power industry are well aware of the problems of disposing of waste heat. Also, waters released by many industrial processes are much hotter than the receiving waters. In some environments, an increase of water temperature can be beneficial. Many important commercial and game fish, such as salmon and trout, live only in cool water. In some instances, the discharge of heated water from a power plant can completely block salmon migration. Higher temperatures also increase the rate of oxygen depletion in areas where oxygen-demanding wastes are present. Water pollution in river. The objective of water quality management is simple to state: to control the discharge of pollutants so that water quality is not degraded to an unacceptable extent below the natural background level. However, controlling waste discharges must be a quantitative endeavor. We must be able to measure the pollutants predict the impact of a pollutant on water quality, determine the background water quality that would be present without human intervention, and decide the levels acceptable for intended uses of the water. The impact of pollution on a river depends both on the nature of the pollutant and the unique characteristics of the individual river. Some of the most important characteristics include the volume and speed of water flowing in the river, the river's depth, the type of bottom, and the surrounding vegetation. Other factors include the climate of the region, the mineral heritage of the watershed, land use patterns, and the types of aquatic life in the river. Water quality management for a particular level river must consider all these factors. Thus, some rivers are highly susceptible to pollutants such as sediment, salt, and heat, while other rivers can tolerate large inputs of these pollutants without much damage. Total maximum daily load. The law requires that these jurisdictions establish priority rankings for waters on the list and develop total maximum daily loads, or the TMDL, for these waters. A TMDL specifies the maximum amount of pollutant that a water body can receive and still meet water quality standards. In addition, the TMDL allocates pollutant loadings, that is the mass of pollutant, that may be contributed among point and non-point sources. The TMDL is computed on a pollutant by pollutant basis for a list of pollutants. Additional categories include acids or bases, measured as pH, pesticides, and mercury. The TMDL computation is defined as what you see on the screen, where WLA is the waste load allocations, that is, portions of the TMDL assigned to existing and future point sources. LAS the load allocations, that is, portions of the TMDL assigned to existing and future non-point sources, and the MOS is the margin of safety. Effects of oxygen-demanding waste on rivers. The introduction of oxygen-demanding material, either organic or inorganic, into a river causes depletion of the dissolved oxygen in the water. This poses a threat to fish and other higher forms of aquatic life if the concentration of oxygen falls below a critical point. However, because oxygen is continuously being replenished from the atmosphere and from photosynthesis by algae and aquatic plants, as well as being consumed by organisms, the concentration of oxygen in the river is determined by the relative rates of these completing processes. Biochemical oxygen demand. If the oxidation of an organic compound is carried out by microorganisms using the organic matter as a food source, the oxygen consumed is known as biochemical oxygen demand, or commonly known as the BOD. The actual BOD is less than the THOD due to the incorporation of some of the carbon into bacterial cells. The test is a bioassay that utilizes microorganisms in conditions similar to those in natural water to measure indirectly the amount of biodegradable organic matter present. Bioassay means to measure by biological means. A water sample is inoculated with bacteria that consume the biodegradable organic matter to obtain energy for their life processes. Because the organisms also utilize oxygen in the process of consuming the waste, the process is called aerobic decomposition. This oxygen consumption is easily measured. While the ultimate BOD increases in direct proportion to the concentration of degradable organic matter, the numeral value of the rate constant is dependent on the following. First is the nature of the waste. There are literally thousands of naturally occurring organic compounds, not all of which can be degraded with equal ease. Simple sugars and starches are rapidly degraded and will therefore have a very large BOD rate constant. Cellulose, for example, toilet paper, degrades much more slowly, and hair and fingernails are almost undegradable and in the BOD test or in normal wastewater treatment. Other compounds are intermediate between these extremes. Second one is the ability of organisms to utilize waste. Any given microorganism is limited in its ability to utilize organic compounds. As a consequence, many organic compounds can be degraded by only a small group of microorganisms. In a natural environment receiving a continuous discharge of organic waste, that population of organisms which can most efficiently utilize this waste will predominate. However, the culture used to inoculate the BOD test may contain only a very small number of organisms that can degrade the particular organic compounds in the waste. Next one is the temperature. Most biological processes speed up as the temperature increases and slows down as the temperature drops. Because oxygen utilization is caused by the metabolism of microorganisms, the rate of utilization is similarly affected by temperature. Ideally, the BOD rate constant should be experimentally determined for the temperature of the receiving water. Graphical determination of BOD constants. A variety of methods may be used to determine K and LO from an experimental set of BOD data. The simplest and least accurate method is to plot BOD versus time. The ultimate BOD is estimated from the asymptote of the curve. The rate equation is used to solve for K. It is often difficult to fit an accurate hyperbola to data that are frequently scattered. Methods that linearize the data are preferred. The usual graphical methods for first-order reactions cannot be used because the semilog plot requires knowledge of the initial concentration, which in this case is one of the constants we are trying to determine, that is LO. One simple method around this impasse is called Thomas graphical method. The method relies on the similarity of the series expansion of the following two functions, just like this. Laboratory measurement of biochemical oxygen demand. In order to have as much consistency as possible, it is important to standardize testing procedures when measuring BOD. In the paragraphs that follow, the standard BOD test is outlined with emphasis placed on the reason for each step rather than the details. The detailed procedures can be found in standard methods for the examination of water and wastewater, which is the authoritative reference of testing procedures in the water pollution control field. So step 1, a special 300 ml BOD bottle is completely filled with a sample of water that has been appropriately diluted and inoculated with microorganisms. The bottle is then stoppered to exclude air bubbles. Samples require dilution because the only oxygen available to the organisms is dissolved in the water. The most oxygen that can dissolve is about 9 milligrams per liter, so that the BOD of the diluted sample should be between 2 and 6 milligrams per liter. Samples are diluted with a special dilution water that contains all of the trace elements required for bacterial metabolism so that degradation of the organic matter is not limited by lack of bacterial growth. The dilution water also contains an inoculum of microorganisms so that all samples tested on a given day contain approximately the same type and number of microorganisms. The ratio of undiluted to diluted sample is called the sample size, usually expressed as a percentage while the inverse relationship is called the dilution factor. Mathematically, these are that what you see on the screen. The appropriate sample size to use can be determined by dividing 4 milligrams per liter, or the midpoint of the desired range of diluted BOD, by the estimated BOD concentration in the sample being tested. A convenient volume of undiluted sample is then chosen to approximate to this sample size. Step 2. Blank samples containing only the inoculated dilution water are also placed in BOD bottles and stoppered. Blanks are required to estimate the amount of oxygen consumed by the added inoculum of microorganisms called seed in the absence of the sample. Step 3. The stoppered BOD bottles containing diluted samples and blanks are incubated in the dark at 20 degrees Celsius for the desired number of days. For most purposes, the standard time of 5 days is used. To determine the ultimate BOD and the BOD rate constant, additional times are used. The samples are incubated in the dark to prevent photosynthesis from adding oxygen to the water and invalidating the oxygen consumption results. As mentioned earlier, the BOD test is conducted at a standard temperature of 20 degrees Celsius so that the effect of temperature on the BOD rate constant is eliminated and results from the different laboratories can be compared. Step 4. After the desired number of days has elapsed, the samples and blanks are removed from the incubator and the dissolved oxygen concentration in each bottle is measured. Nitrogen oxidation. Actually, many organic compounds, such as proteins, also contain nitrogen that can be oxidized with the consumption of molecular oxygen. However, because the mechanisms and rates of nitrogen oxidation are distinctly different from those of carbon oxidation, the two processes must be considered separately. Logically, oxygen consumption due to oxidation of carbon is called carbonaceous BOD, or the CBOD, while that due to nitrogen oxidation is called nitrogenous BOD, or the NBOD. The organisms that oxidize the carbon in organic compounds to obtain energy cannot oxidize the nitrogen in these compounds. Instead, the nitrogen is released into the surrounding water as ammonia. At normal pH values, this ammonia is actually in the form of the ammonium cation. The ammonia released from organic compounds plus that from other sources such as industrial waste and agricultural runoff, that is fertilizers, is oxidized to nitrate by a special group of nitrifying bacteria as their source of energy in a process called nitrification. Next is the Streeter-Phelps DO-SAG curve. As long as the discharge of oxygen-demanding wastes is well within the self-purification capacity, the DO level will remain high and a diverse population of plants and animals, including game fish, can be found. As the amount of waste increases, the self-purification capacity can be exceeded, causing detrimental change in plant and animal life. The stream loses its ability to cleanse itself and the DO level decreases. When the DO drops below about 4 to 5 milligrams per liter, most game fish will have been driven out. If the DO is completely removed, fish and other higher animals are killed or driven out and extremely nauseous conditions result. The water becomes blackish and foul-smelling as the sewage and dead animals' life decompose under anaerobic conditions, that is, without oxygen. One of the major tools of water quality management in rivers is the ability to access the capability of a stream to absorb a waste load. This is done by determining the profile of DO concentration downstream from a waste discharge. This profile is called the DO-SAG curve because the DO concentration dips as oxygen-demanding materials are oxidized and then rises again further downstream as the oxygen is replenished from the atmosphere. So here are the other factors affecting DO levels. First is the mass balance approach. Simplified mass balance helps us understand and solve the DO sag curve problem. 3. Conservative, those without chemical reaction, mass balances may be used to account for initial mixing of the waste stream and the river. DO, carbonaceous BOD, and temperature all change as the result of the mixing of the waste stream and the river. Once these are accounted for, the DO sag curve may be viewed as a non-conservative mass balance, that is, one with reactions. Second is the oxygen deficit. The DO sag equation has been developed using oxygen deficit rather than dissolved oxygen concentration to make it easier to solve the integral equation that results from the mathematical description of the mass balance. The oxygen deficit is the amount by which the actual dissolved oxygen concentration is less than the saturation value with respect to oxygen in the air. Next is the initial deficit. The beginning of the DO sag curve is at the point where a waste discharge mixes with the river. The initial deficit is calculated as the difference between saturated DO and the concentration of the DO after mixing. Next is the deoxygenation rate constant. The deoxygenation rate constant differs from the BOD rate constant because there are physical and biological differences between a river and a BOD bottle. Next is reaeration. The value of K depends on the degree of turbulent mixing, which is related to stream velocity and on the amount of water surface exposed to the atmosphere compared to the volume of water in the river. O'Connor and Dobbins in 1958 developed a generalized empirical equation to estimate the reaeration constant based on the characteristics of the stream and the molecular diffusion of oxygen into water. Travel time. With the speed of the flow in the river and the distance downstream, the travel time may be estimated from the basic relationship between time, distance, and speed, which is T is equal to distance over speed. Another is the critical point. The lowest point in the DO sag curve, which is called the critical point, is of major interest since it indicates the worst conditions in the river. The time to the critical point can be found by differentiating the equation, setting it equal to 0, and solving for t using base E values for K and KD. Interpreting results. Modeling equations may predict impossible results. This is true for the Streeter-Phelps model. For example, if the deficit calculated from the equation is greater than the DO saturation, the result will be a negative number because it is physically impossible for the DO to be less than 0. This means that all the oxygen was depleted at some point upstream and the DO is 0. Assuming your calculations are correct, you must use your engineering judgment and report it as 0 because it cannot be less than 0. Management strategy. The beginning point for water quality management in rivers using the DO sag curve is to determine the minimum DO concentration that will protect the aquatic life in the stream. This value, called the DO standard, is generally set to protect the most sensitive species that exist or could exist in a particular river. For a known waste discharge and a known set of river characteristics, the DO sag equation can be solved to find the DO at the critical point. If this value is higher than the standard, the stream can adequately assimilate the waste. If the DO at the critical point is less than the standard, then additional waste treatment is needed. Nitrogenous BOD. Up to this point, only carbonaceous BOD or the CBOD has been considered in the DO sag curve. However, in many cases, nitrogenous BOD or the NBOD has at least as much impact on dissolved oxygen levels. Modern wastewater treatment plants can routinely produce effluents with CBOD of less than 30 milligrams per liter. Other factors affecting DO levels in rivers. The classical DO sag curves assumes that there is only one point source discharge of waste into the river. In reality, this is rarely the case. Multiple point source can be handled by dividing the river up into reaches with a point source at the head of each reach. A reach is a length of river specified by the engineer on the basis of its homogeneity, that is, channel shape, bottom composition, slope, and so forth. The oxygen deficit and residual BOD can be calculated at the end of each reach. Effects of nutrients on water quality in rivers. Although oxygen-demanding wastes are the most important river pollutants on an overall basis, nutrients can also contribute to deteriorating water quality in rivers by causing excessive plant growth. Nutrients are those elements required by plants for their growth. They include, in order of abundance in plant tissues, carbon, nitrogen, phosphorus, and a variety of trace elements. When there are sufficient quantities of all nutrients available, plant growth is possible. By limiting the availability of one nutrient, further plant growth is prevented. The availability of nutrients is not the only requirement for plant growth. In many rivers, the turbidity caused by eroded soil particles, bacteria, and other factors prevents light from penetrating far into the water, thereby limiting total plant growth in deep water. It is for this reason that slime growth on rocks usually occur in shallow water. Strong water currents also prevent rooted plants from taking hold and thus limit their growth to quiet backwaters where the currents are weak and the water is shallow enough for light to penetrate. So the effects of nitrogen. There are three reasons why nitrogen is detrimental to receiving body. Number one, in high concentration, NH3N is toxic to fish. Second, NH3 in low concentration and NO3 serve as nutrients for excessive growth of algae. Third, the conversion of NH4 to NO3 consumes large quantities of dissolved oxygen. Effects of phosphorus. The major deleterious effect of phosphorus is that it serves as a vital nutrient for the growth of algae. If the phosphorus availability meets the growth demands of the algae, there is an excessive production of algae. When the algae die, they become an oxygen-demanded organic material as bacteria seek to degrade them. This oxygen demand frequently overtaxes the DO supply of the water body and, as a consequence, causes fish to die. Management strategy. The strategy for managing water quality problems associated with excessive nutrients is based on the sources for each nutrient. Except under rare circumstances, there is plenty of carbon available for plant growth. Plant use carbon dioxide, which is available for the bicarbonate alkalinity of the water and from the bacterial decomposition of organic matter. As carbon dioxide is removed from the water, it is replenished from the atmosphere. Water pollution in lakes. Oxygen-demanding waste can also be important lake pollutants, especially when the waste is discharged to a contained area such as a bay. Pathogens are of particular concern near bathing beaches. Again, as with rivers, there are special classes of lakes which are most seriously affected by other pollutants such as toxic chemicals from industrial discharges. However, phosphorus dominates other pollutants in controlling water quality in the vast majority of lakes that we will give it special emphasis. A knowledge of lake systems is essential to an understanding of the role of phosphorus in lake pollution. The study of lakes is called limnology. This section is essentially a short course in limnology as it relates to phosphorus pollution. Stratification and turnover. Nearly all lakes in the temperature climatic zone become stratified during the summer and overturn or turn over in the fall due to changes in the water temperature that result from the annual cycle of air temperature changes. In addition, lakes in cold climates undergo winter stratification and spring overturn as well. These physical processes, which are described below, occur regardless of the water quality in the lake. Nonetheless, they do help determine the water quality. Biological zones. Lakes contain several distinct zones of biological activity, largely determined by the availability of light and oxygen. The most important biological zones are the euphotic, littoral, and benthic zones. Euphotic zone, the upper layer of water through which sunlight can penetrate, is called the euphotic zone. All plant growth occurs in this zone. In deep water, algae are the most important plants, while rooted plants grow in shallow water near the shore. Depth of the euphotic zone is determined by the amount of turbidity blocking sunlight penetration. Below the euphotic zone is the profundal zone. The transition between the two zones is called the light compensation level. The light compensation level corresponds roughly to a depth at which the light intensity is about 1% of unattenuated sunlight. It is important to note that the bottom of the euphotic zone only rarely coincides with the thermocline. The littoral zone. The shallow water near the shore in which rooted water plants can grow is called the littoral zone. The extent of the littoral zone depends on the slope of the lake bottom and the depth of the euphotic zone. The littoral zone cannot extend deeper than the euphotic zone. The last one is the benthic zone. The bottom sediments comprise the benthic zone. As organisms living in the overlying water die, they settle to the bottom where they are decomposed by organisms living in the benthic zone. Bacteria are always present. The presence of higher life forms such as worms, insects, and crustaceans depends on the availability of oxygen. Lake productivity. The productivity of a lake is a measure of its ability to support a food web. Algae form the base of the food web, supplying food for the higher organisms. A lake's productivity may be determined by measuring the amount of algal growth that can be supported by the available nutrients. Although a more productive lake usually will have a higher fish population, the number of the most desirable fish may decline. In fact, increased productivity generally results in reduced water quality because of undesirable changes that occur as algal growth increases. Because the important role productivity plays in determining water quality, it forms a basis for classifying lakes. So here are some kinds or types of lakes. First is the oligotrophic lakes. Oligotrophic lakes have a low level of productivity due to a severely limited supply of nutrients to support algal growth. As a result, the water is clear enough that the bottom can be seen at considerable depths. In this case, the euphotic zone often extends into hypolimnion, which is aerobic. Oligotrophic lakes therefore support cold water game fish. Lake Tahoe on the California-Nevada border is a classic example of an oligotrophic lake. The next is the eutrophic lakes. Eutrophic lakes have a high productivity because of an abundant supply of algal nutrients. The algae cause the water to be highly turbid, so the eutrophic zone may extend only partially into the epilimnion. As the algae die, they settle to the lake bottom where they are decomposed by benthic organisms. Another is the mesotrophic lakes. Lakes which are intermediate between oligotrophic and eutrophic are called mesotrophic. Although substantial depletion of oxygen may have occurred in the hypolimnion, it remains aerobic. Senescent lakes. These are very old, shallow lakes which have thick organic sediments and rooted water plants in great abundance. These lakes will eventually become marshes. Eutrophication. Eutrophication is a natural process in which lakes gradually become shallower and more productive through the introduction and cycling of nutrients. Thus, oligotrophic lakes gradually pass through the mesotrophic, eutrophic, and senescent stages, eventually filling completely. In some lakes, the eutrophication process is so slow that thousands of years may pass with little change in water quality. Other lakes may have been eutrophic from the day they were formed if nutrient levels were high at that time. Cultural eutrophication is caused when human activity speeds the processes naturally occurring by increasing the rate at which sediments and nutrients are added to the lake. Algal growth requirements. All algae require macronutrients such as carbon, nitrogen, and phosphorus, and micronutrients such as a trace element. For algae to grow, all nutrients must be available. Lack of any one nutrient will limit the total algal population. The availability of each nutrient and its natural cycle are summarized as follows. First is the carbon. Algae obtain their carbon from carbon dioxide dissolved in the water. Because the carbon dioxide is in equilibrium with the bicarbonate buffer system, the immediately available carbon is determined by the alkalinity of the water. However, as carbon dioxide is removed from the water, it is replenished from the atmosphere. The nitrogen. Nitrogen in lakes is usually in the form of nitrate and comes from external sources by way of inflowing streams or groundwater. When taken up for algal growth, the nitrogen is extremely reduced to amino nitrogen and incorporated into organic compounds. When dead algae undergo decomposition, the organic nitrogen is released to the water as ammonia. The ammonia is then oxidized back to nitrate by bacteria in the same nitrification process discussed earlier in river systems. Next is the phosphorus. Phosphorus in lakes originates from external sources and is taken up by algae in the inorganic form and incorporated into organic compounds. During algal decomposition, phosphorus is returned to the inorganic form. The release of phosphorus from dead algal cells is so rapid that only a little of it leaves the epilimnion with the settling algal cells. The last one is the trace elements. The quantities of trace elements required to support algal growth are so small that most fresh waters have sufficient amounts for a substantial algal population. The limiting nutrient. In 1840, Justin Liebig formulated the idea that growth of a plant is dependent on the amount of foodstuff that is presented to it in the minimum quantity. This is now known as Liebig's law of the minimum. As applied to algae, it means that the algal growth will be limited by the nutrient that is least available. Of all the nutrients, only phosphorus is not readily available from the atmosphere or the natural water supply. For this reason, phosphorus is deemed the limiting nutrient in lakes. Control of phosphorus in lakes. Because phosphorus is usually the limiting nutrient, control of cultural eutrophication must be accomplished by reducing the input of phosphorus to the lake. Once the input is reduced, the phosphorus concentration will gradually fall as phosphorus is buried in the sediment or flushed from the lake. To be able to reduce phosphorus inputs, it is necessary to know the sources of phosphorus and the potential for their reduction. The natural source of phosphorus is the weathering of rock. Phosphorus released from the rock can enter the water directly, but more commonly it is taken up by plants and enters the water in the form of dead plant matter. It is exceedingly difficult to reduce the natural inputs of phosphorus. Municipal and industrial waste waters. All municipal sewage contains phosphorus from human excrement. Many industrial wastes are high in this nutrient. In these cases, the only effective way of reducing phosphorus is through advanced waste treatment processes. Septic tank seepage. The shores, the shores of many lakes are dotted with homes and summer cottages, each with its own septic tank and tile field for waste disposal. As treated, wastewater moves through the soil toward the lake. Phosphorus is absorbed by the soil particles, especially clay. Thus, during the early life of the tile field, very little phosphorus gets to the lake. However, with time, the capacity of the soil to absorb phosphorus is exceeded, and any additional phosphorus will pass on into the lake, contributing to eutrophication. Agricultural runoff. Because phosphorus is a plant nutrient, it is an important ingredient in fertilizers. As rainwater washes off fertilized fields, some of the phosphorus is carried into streams and then into lakes. Most of the phosphorus not taken up by growing plants is bound to soil particles. Bound phosphorus is carried into streams and lakes through soil erosion. Acidification of lakes. Pure rainwater is slightly acid. As we discussed in the previous chapters, carbon dioxide dissolves in water to form carbonic acid. The equilibrium concentration of carbonic acid results in a rainwater which has a pH of approximately 5.6. Thus, acid rain is usually defined to be precipitation with a pH less than 5.6. The northeastern US and Canada frequently record rainwater pH values between 4 and 5. These low pH values have been attributed to emissions of sulfur and nitrogen oxides from the combustion of fossil fuels. Most lakes are buffered by the carbonate buffer system. To the extent that the buffer capacity of the lake is not exceeded, the pH of the lake will not be appreciably affected by acid rain. If there is a source of carbonate to replace the consumed by the acid rain, the buffering capacity can be quite large. Calcareous soils are those containing large quantities of calcium carbonate. Water pollution in estuaries. Ground pollution. Groundwater, by its very location, has a large measure of protection from contaminants that are found in surface waters. However, once the groundwater becomes contaminated, its location and low rate of replacement with fresh water makes it difficult to return it to the pristine state. Two major sources of contaminants are of concern: uncontrolled releases of biological and chemical contaminants, and salt water intrusion from overpumping of wells. Uncontrolled releases. Uncontrolled releases come from a variety of sources. Maybe discharge from improperly operated or located septic systems, leaking underground storage tanks, improper disposal of hazardous or other chemical waste, spills from pipelines or transportation accidents, recharge of groundwater with contaminated surface water, and or leaking landfills or retention ponds or lagoons. Saltwater intrusion. Fresh water aquifers near oceans or above saline aquifers may become contaminated with salt water when water is pumped from wells that draw water that is too close to the freshwater salt water interface. And that will be all about the water pollution for this video. Thank you for watching.